Hello everyone and welcome to Control Engineering and Programming tutorials. In these tutorials we present real and applicable knowledge of control engineering, programming, machine learning, optimization, robotics, and mechatronics. This channel is very unique and special since we are trying to bridge a gap between theory and practice. On this YouTube channel you can find videos explaining how complex algorithms are derived from scratch. And in addition to this, you can also find videos explaining how these algorithms are implemented in C++, MATLAB, or Python. In this important video tutorial, we explain how to implement the Kalman filter from scratch in C++ by using the Eigen matrix library. The purpose of this video is to teach you how to write a code in a disciplined manner and to write a code that is easily reusable. By the end of this video tutorial, you will learn how to generate these nice graphs. These graphs illustrate the convergence of the Kalman filter. Moreover, they compare two implementations. One implementation is in Python and another implementation is in C++. Since in this video tutorial I'm explaining a very complex topic, I will split this video tutorial into 2 or 3 parts. Currently you're watching the first part. But before I start with the explanations, I would like to briefly mention the following. It took me a significant amount of time, energy and planning to create this video tutorial, as well as other free video tutorials that you can find on my channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, let's start. Here's a brief summary of the Kalman filter equations that we need to implement in C++. The Kalman filter consists of 2 steps. Step 1 and Step 2. In the first step, we propagate the a posteriori estimate, denoted like this, and the a posteriori covariance matrix of the estimation error, denoted like this. We propagate these 2 quantities through the corresponding equations that describe the dynamics of the state and the dynamics of the covariance matrix. As the main result of this step, we obtain 2 quantities. The first quantity is the a priori state estimate for the time step k and the a priori covariance matrix for the time step k. Let's summarize. At the time step k-1, we have the knowledge of the a posteriori estimate, denoted like this, and the a posteriori covariance matrix, denoted like this. Then, by using these 2 quantities and these 2 equations, we compute, for the time step k, the a priori estimate, denoted by xk minus hat, and the a priori covariance matrix, denoted by pk minus. In step number 2, we first obtain the measurement yk. Then, by using this measurement and the a priori estimate xk minus hat and the a priori covariance matrix pk minus, we compute these quantities. Capital K with an index k is the Kalman gain matrix. xk plus hat is the a posteriori estimate for the time step k, and pk plus is the a posteriori covariance matrix. After we explain the Kalman filter equations, let's proceed with C++ implementation. In this video tutorial, I'm using the VS Code editor to write and compile the C++ code. I created a video tutorial that explains how to install the VS Code editor and how to compile the Eigen C++ library in VS Code editor. I included these tutorials in the description below this video tutorial, and consequently, if you're not familiar with the VS Code editor and if you don't know how to install or to compile the Eigen C++ library in VS Code editor, I strongly suggest you to watch these videos. The C++ code files that I will explain in the sequel of this video are posted on my GitHub page. A link to the GitHub page is given in the description below this video. Your first assignment is to go to my GitHub page and to download the code files. Then, create a folder, in my case the name of the folder is Kalman, and copy all the files to that new folder. At the end, you will see these 6 files. Let's briefly explain these files. This is the header file for the Kalman filter class, this is the implementation file for the Kalman filter class, and this is the driver code that explains how to use the Kalman filter class. On the other hand, we have these 2 Python code files. This file implements the Kalman filter in Python, and this is the driver code. On the other hand, we also have this CSV file. This CSV file is necessary for compiling the C++ code. I will explain this file later on in the video. In order to be on the safe side and in order to have some baseline for comparison, I also implemented the Kalman filter in Python. My results show that the Python and C++ implementation produce the same convergence result. Consequently, I'm 100% sure, or better to say 99.999% sure, that my C++ implementation of the Kalman filter is correct. Under the assumption that you have properly installed the Microsoft Visual Studio as well as VS Code Editor, if you click here on Start and if you type Developer, you'll see this command prompt. Open this command prompt. Next, let us go to newly created folder. The name of the folder is Kalman. Consequently, we will type cd Kalman. We can see all the files over here. Next, let's start the VS Code editor. We will type code with a dot. And voila, here's our VS Code editor. Open this file. In order to properly set up the VS Code environment and in order to set up the compiler, we need to create 2 JSON files. In my opinion, the easiest way to create these files is to try to compile this code. We know that we will not be able to compile this code. However, after trying to compile the code, we will see the first file. So let's do that by clicking over here. We will select the standard compiler and let's see the output. Of course, we will see errors. However, we are not interested in errors. And for us, the most important thing is this folder over here. So open this folder, and inside of this folder, you will see this file, tasks.json. Over here are the arguments of our compiler. The compiler is cl.executable. Next, we need to tell to our compiler where the header files of our Eigen C++ library. For that purpose, I will add comma over here and start a new line, and I will simply paste my path. The path to my Eigen C++ header files is this one. Let us verify this path. C, toolbox, Eigen 3.4.0, and consequently, let's verify the path is correct. This option dash with a capital I tells the compiler to include this folder while compiling the source code. Okay, this was the first JSON file. To create the second JSON file, I will press Ctrl, hold Ctrl, press Shift, hold Shift, and press P. You will see this option. Again, Ctrl, Shift, P. This window will pop up. Click over here, and immediately you can see another JSON file over here. Next, let's open and edit this file. Click on this file, and over here we need to include the path to our Eigen C++ header files. Again, comma, new line, and here's the path. Note over here that I don't need the option dash include, and save this file. Okay, let's try to compile the code at this point. Open driver code Kalman CPP, and let's try to compile this file, and hopefully everything should work. Let's see. Okay, so far so good. Let's see the Explorer, and immediately you will see several files over here that I will explain in the second part of this video. First, let's explain the header file. Consequently, open the header file. We need to include string, and over here we need to include Eigen C++ matrix library. After that, you also have to specify that you are using namespace Eigen. Of course, we need to specify that we're using namespace std, and here are the private member variables of our class. This variable is used to track the progress of the Kalman filter iteration, and it directly corresponds to this subscript k. First, we will open and explain our header file. Here's the header file. We first include string library, then we include the Eigen C++ library, and we need to use the namespace Eigen as well as std. Let's look into the private member variables. The variable k is used to track the current time step of the estimator, and this variable directly corresponds to the subscript k in these equations. These variables m, n, and r correspond to input, state, and output dimensions respectively. Over here we declare that our matrices are of the type matrix XD. Matrix XD is an eigentype definition for matrix consisting of doubles, and these two parameters mean that the matrices do not have fixed dimensions. That is, we will later on adjust the matrix dimensions. The matrices A, B, and C are the system matrices A, B, and C, and notice over here that in my implementation I'm assuming that the matrices are not time varying. Consequently, I don't have the index of k in these matrices. Then the matrices Q and R are the covariance matrices of the disturbance and of the measurement noise, and they are given over here, Q and R. And finally, P0 is the initial guess of the state covariance matrix. P0 corresponds to this matrix, that is, better to say for the a posteriori matrix, for k is equal to 0. The vector x0 is an initial guess of our estimate, and note over here that I declared this vector as matrix XD eigendata type. I can do that since vectors are actually matrices, and later on I will adjust dimensions of this matrix such that it's basically a column vector. Next, let's explain this matrix. This matrix will have the following structure. It will be a fat matrix. The first entry of this matrix will be x0 plus hat. The second one will be x1 plus hat until the end. Let's say we have n estimates, and these estimates are denoted like this. That is, this matrix will store all the a posteriori state estimates column-wise. Similarly, this matrix will store all a priori state estimates starting from x1 minus hat and until x n minus hat. This matrix will store the a posteriori covariance matrices starting from P0 plus, this is the first entry, the second entry is P1 plus, until Pn plus. Similarly, this matrix will store the a priori covariance matrices starting from P1 minus, then the second entry, or better to say block entry, will be P2 minus until Pn minus. This matrix will store the Kalman filter gain matrices starting from K1, then we have K2 until Kn. And finally, this matrix will store the estimation errors. The estimation errors are defined like this, and they correspond to this part over here. This is our estimation error. That is, this is Ek. Going back to our code, this will be a fat matrix with the first entry E1, then we will have E2 until En. Next, let's explain the member functions. This is the default constructor, and currently this is just an empty function. I need to edit and improve this default constructor later on. This is the overloaded constructor that I'm actually using, and let's analyze this constructor. It takes as an input the matrices A, B, C, Q, R, P0, the vector x0, and this parameter max simulation samples. And let's look into the implementation of this overloaded constructor. For that purpose, let's open the implementation file. Here's our overloaded constructor. We immediately see that we set k is equal to 0, and if we go back to our summary, we are basically initializing our filter by setting k is equal to 0. Okay, then we simply assign the private variables a is equal to a input, b is equal to b input, etc. Then we extract the appropriate dimensions. N is equal to the state dimension, that is the number of rows of our A matrix, M is equal to the number of columns of our B matrix, and R is equal to the number of rows of our C matrix. As I mentioned previously, the matrix with the name estimates a posteriori is used to store the a posteriori estimates column-wise. First, I resize this matrix. The matrix will have n number of rows, that is, the number of rows should be equal to the state dimension, and the number of columns is equal to this parameter max simulation samples. This parameter is provided as the input to our overloaded constructor. Next, I set all of the matrix entries to 0, 0, 0, 0, 0, 0, 0, 0. I do that to pre-allocate the space for this matrix and to make this code as efficient as possible, since I don't want to dynamically update the size of this matrix. Finally, I say that the first column of this matrix is actually our initial state estimate denoted by x0. Consequently, later on, we will update other columns of this matrix. In the same manner, I define the matrix estimates a priori. This matrix is used to store the a priori estimates column-wise. I just resize this matrix to the appropriate dimensions, and I set all of its entries equal to 0. By using the same logic, I define all other matrices. This matrix, that's called covariance a posteriori, is used to store the a posteriori covariance matrices. I resize the matrix to appropriate dimensions, I set all of the entries to be equal to 0, and I say that the first block of this matrix is equal to P0. In the same manner, I define this matrix called covariance a priori. This matrix is used to store the a priori covariance matrices next to each other. Consequently, this matrix will store P1 minus, P2 minus, etc. In the same manner, I define the matrix that will be used to store the Kalman gain matrices, and I define the matrix that will be used to store the errors. These errors are also called innovations. And that's our overloaded constructor. It simply takes the matrices and this parameter, and it properly initializes and defines our private member variables. Let's go back to our header file and let's explain other member functions. First, we will explain this function called predict_estimate. This member function predicts the estimates on the basis of the external input. It computes the a priori estimate and it computes the a priori covariance matrix. That is, it implements these two equations and the step number 1. Let's look into the implementation of this function. Here's the function. The function is relatively simple. The input argument is the external input, that is, it's the input uk-1, and this function computes the a priori estimate for the time step k, and it computes the a priori covariance matrix for the time step k. You can see over here the beauty of the Eigen C++ matrix library. We can simply type a star estimates a posteriori, we specify the corresponding column of this matrix, and it's very simple. In the same manner, we can compute covariance a priori. We just select the appropriate block that we want to update, then we use basic matrix computations and operations to compute the a priori matrix. Next, let's go back to our header file and let's explain this function called update_estimate. This member function updates the estimate on the basis of the measurement. It computes the Kalman filter gain, it computes the a posteriori estimate, and it computes the a posteriori covariance matrix. That is, this function implements the step number 2, that is, it implements these 3 equations. Okay, so let's look into this member function. Let's open the implementation file, and here's the function. This function sk corresponds to this inverse. That is, this part is sk. Once we compute sk, and you can see over here how we do that, we can compute the gain matrices. That is, we compute the corresponding block of our gain matrices matrix. We can simply take the covariance matrix a priori, that is, we take the corresponding block, we multiply this block by C transpose, and we multiply the result by sk. And that's exactly this expression over here. Next, we need to compute the error. This is the error. We take the measurement is the input to this function, and we simply compute this part, and finally we update the errors matrix, the corresponding column. Finally, we compute the a posteriori estimate, and remember here that k starts from 0, and the corresponding columns is x0, that is the initial guess. Consequently, we have something like this, and this expression over here is exactly this part over here. Finally, we need to compute the a posteriori covariance matrix, and we do it over here. First, we need to compute this matrix, I minus kc. It's precisely this matrix, I minus k times c, that is, it's this part over here, I minus ck. Once we compute that matrix, we can simply perform matrix multiplication. We take I minus kc, we multiply it with the corresponding block of the covariance a priori matrix, and we finally add this part, gain matrix times R times gain matrix transpose. And that's exactly this part over here. And that's it. That was our function update estimate. Let's go back to our header file. This function OpenData is used to load the measurement data from the external CSV file. Let's explain this. I will generate the measurement data for my Kalman filter by using a Python script that I will explain in my next video. The measurement data will look like this. They will be grouped in a column vector, and for example, this is the first measurement, 0.1, then minus 0.2, 0.3, etc. This vector will be generated in Python. Then in Python, I will save this vector as CSV or comma separated value file. This function will read this file, will go through the rows of this file and this vector, and it will create a matrix that will be used as the output matrix for my Kalman filter. And in the Kalman filter iteration, I will read every row of this matrix, and I will provide every row as an input to my corresponding function, and in this case the name of the function is update estimate. Again, what will happen over here? The rows from this comma separated value file, for example, this row, or the third row, until, for example, the nth row, will be fed to the update estimate function that will compute the updated estimate and the updated covariance matrices. Finally, once the Kalman filter computes all the estimates and all the covariance matrices, we will save the data by using this function. This function will produce several CSV files, and the names of the files will be given by these strings. It will produce 1, 2, 3, 4, 5, 6 files. That is, all the important data that quantify the convergence of the Kalman filter will be saved in the corresponding CSV files. The implementation, or better to say implementations of these files or these functions are given over here, and they are relatively complex, and I will not explain them in this video. There is a video tutorial that I made maybe 2 or 3 years ago that explain how to implement these functions. These video tutorials are given in the description below this video tutorial. Finally, let's look into the driver code of our Kalman filter, and let's explain the driver code. Here's the driver code. We include input-output stream library, and then we include the header file and the implementation file of our Kalman filter class. We are using namespace std and namespace Eigen. First, we define our model. Over here, I define my A, B, and C matrices, and These matrices will be explained in more details in the second part of this video, so don't worry for the time being if you don't understand what is the discretization time step, measurement noise, standard deviation, etc. Everything will be explained in the second part of this video. Then, I define my covariance matrix, that is the initial guess of the covariance matrix. I define covariance matrix of the measurement noise, and I define the covariance matrix of the state disturbance. Then I specify the guess of the initial state, and this is how we do all these steps in Eigen C++. Over here you can uncomment these lines. If you want to verify that the matrices are properly defined, you can simply use the cout command to print them in your terminal. The next step is to define a matrix that will store all the measurements. I will read this file output.csv, and I will use the function OpenData. This function will fill in the columns of the matrix output noisy. And just as a small disclaimer, this file is actually produced by the Python script that I will explain in the second part of this video. Once I do that, I extract the number of rows of my output noisy matrix, and just for verification I print it out. Then I define the max data samples to be sample number, and remember that sample number is the number of rows of the output noisy matrix, and I add 10. Let's go back now to our overloaded constructor. I specify this number, and you can see why I add plus 10, because I want to be on the safe side, because at the end of the day this overloaded constructor will resize the matrices according to this parameter, and I want to make sure that I have enough space to store all the entries. That's why I add plus 10. Okay, let's go back to our driver code. Over here I specify my input and output matrices. However, they are simply scalars since my system has only a single input and single output. You can see that my matrix C is simply a row matrix and matrix B is simply a column matrix. Consequently, I have one input and one output. In this for loop, I run the Kalman filter. Since I don't have inputs in my system, input is always equal to 0. And the output, as you can see over here, is equal to the corresponding row of my output noisy matrix. This index that's iterated in this for loop simply goes through the rows of my output noisy matrix. And keep in mind again that the output noisy matrix is a matrix formed on the basis of the measurements that are generated in the Python script. Once I create this scalar output y, and output y has to be of the type matrix xd, I simply called predict estimate, right? Here's my Kalman filter object. I call the predict estimate, I specify the input is actually 0, and after I do that, I call the update estimate step, and I repeat this in this for loop. So this for loop will just loop until sample number -1 is reached, and we are done. The Kalman filter iteration has completed, and then we can simply save the data. We save the a posteriori, a priori estimates, covariance matrices, gain matrices, and errors. And that's it. Okay, that will be the end of the first part of this video tutorial. I will explain in the second part of this tutorial how to use this code together with the Python script, and I will provide more implementation details. If you like this video, please press the like and subscribe buttons. Thank you very much and have a nice day.